Well, that's good. That means we get out early. Okay.
And B bars this.
I'd rather things be on tonight. That way it
Then I think this one single matrix equation can be represented as augmented matrix. It looks like this. You know, actually today, one of my new techniques will involve using the identity matrix to solve the system.
Okay, yeah.
Chris?
You said on Thursday that you would tackle this on Monday today. I'm a little bit confused, just slightly confused about how creating an augmented matrix of some matrix A and the identity matrix of the same size and performing some Gauss-Jordan elimination will eventually yield the inverse matrix through that method. And I sort of, I mean, correct me if I'm wrong, but I get this feeling that by doing that elimination and sort of finagling your identity matrix, or finagling your matrix A to look like an identity matrix, is in a way undoing the linear transformation on your identity matrix, which will give you the inverse operation. I'm not really sure. And it just sort of really rigorous way to show that just doing that will give you the inverse.
Before I answer your question, can I say this though? I need to stipulate that not every square matrix has an inverse. So I'm going to rephrase things a little bit. If the matrix does have an inverse, then it is going to be the case that my steps gives you that matrix. You guys, I'm sorry. In my last class, I went and did my homework. I went and got a black pen, but I won't put it in there. Shoot. That's a little better.
I like your suit, by the way.
Thank you very much.
A lot of comments on that today.
Don't be very careful. Do not be specific. Talk general. What have I just done? What have I just done? I see where you say. I guess so. If this were an augmented matrix, I guess you can refer to it as really applying the steps of Gauss-Jordan elimination. I would say this slightly differently in English. All I've really done was I reduced the original matrix. I completely reduced it. I put it in reduced row echelon form. I transform it into the identity matrix. As a matter of fact, using the office notation, actually from here to here, what I really did was in English, I added negative, did I write that right?
Negative row 1 to negative to
3
row
times
2.
the first row. Added to second, use the result of my new second row. Using the using the office notation. I never do this. Apologies. I added negative 3 times the first row to the second row.
So
That's the first step.
can you just briefly explain that notation? Because I know you
Yeah.
went over it on Saturday, but I went home.
The author does it this way. He says, if I've got a sub I, j, I've got a number in here, k, he really just means this. He's taking k, multiplying to the ith row, adding to the jth row, and using it as a new jth row.
Okay.
That's all he means by that notation.
Okay.
And I just maintain my second step was, well actually, my second step was merely taking the second row and multiplying by negative 1/2. And I think my last step was merely, actually what was it? Was it multiplying negative 2 to the second row, adding it to the first row? However,
So you use your A's for addition, M's for multiplication, basically?
yeah, in his notation, he would use an uppercase P if he wanted to commute 2 rows. See, he's
Okay.
got P's, A's, and M's. That's what he has.
Okay. Okay.
I'm not a racist, I need this, Chris, to answer your question, I need this. But let's take care of these individual steps from scratch, but let's do it on the identity matrix. For example, would you guys agree that if I took the identity matrix and I added -3 times the first row to the second row, wouldn't that look like this? I'm starting to slow you guys, jeepers. And if I were to take the identity matrix and I were to multiply the second row by, is it -1/2? Wouldn't that give me this? And lastly, if I were to take -2 times the second row added to the first, but actually did this on the identity matrix, I think it gives me this. Okay, I'll slow down. Is that 1 -201? You guys there so far? And something else. I'm only changing colors and fading. If I were actually to take these beasts and actually multiply them together, let's see what I get. If I took 1 0 -3 1, and then I took 1 0 0 -1/2, and then I took my 1 -2 0 1. If I multiply these out, here's what I get. Let's multiply the last two. And then multiply the last two. Wouldn't that actually give me this? Actually, I don't know what it gives me. Dotting. What about over here? Wouldn't that be -2? You guys getting practice in homework? -1/2. And if I multiply these two together, let's see what I get.
1, 0.
Do I really?
-2. -3. And
Yeah, I gotta slow down too.
6 times a half.
Is that the 11/2? But you know, in multiplying matrices together like this, something really interesting happens. Because I think each and every one of these individual matrices represents something going on in two-dimensional space. For example, I can't. Let's try this one. Here's my x-axis. Here's my y-axis. If I ever had a point down, how about 1, 2? If I were to multiply 1, 2 by the first matrix, is that 1 0 -3 1? Gives me another 2 by 1, which I can interpret as a point or a vector. It doesn't matter which way you say it. And I think what I generate is nothing more than a 1 and a -1. Where's that located? So it's a whole new point of 1, -1? Like down here. Do you guys agree?
Yeah.
What if I took that point 1, 2 multiplied by 1 0 0 -1/2? Now what does that give me?
Gives you 1 and
Oh shoot, I didn't mean for that to happen. Pure coincidence, I didn't mean to be the same thing. They were in this case, but I think the result, however, of multiplying a point by a 2 by 2 matrix of one of these types is I transform a point from somewhere in the Cartesian coordinate system to somewhere else. And I do it in a very special fashion. Chris, I'm cheating. I really am not answering your question fully, only because I'm sticking myself to 2 space, not beyond it. My argument has to be a bit more sophisticated for beyond 2 space. But if I can multiply a point by a matrix and get another point in two space, then I can undo that operation. And I think when you apply your elementary operations to a matrix where you've got a square one augmented with the appropriate size identity matrix, you're talking in two space about nothing more than transferring points in two space in a very special way. And all we're doing is undoing those transformations. It's a reverse process. But you guys, did I ever post that thing I told you I was going to post last time? Remember how I told you I was going to come to class, solve the same darn system that I did last week with Gauss-Jordan elimination? I'm just going to do it in a couple different ways. I don't have a copy, so I'll have to bring it up. Man, for such a new computer, it sure is slow. So if you guys don't mind, I am going to come back to that system just to make sure we get the same answers we did before. And here's my new technique. Guys, can I do something different? There's a lot of tediousness. It's very tedious with the arithmetic. Just so you can really see what I'm doing, can I embarrassingly slip out just to get a decent pen? So you can see what I'm writing. Just give me 1 second. Okay, I'm better armed. So I maintain if I do have a system of linear equations in which this single vector equation or matrix equation models it, that if I had something called an inverse matrix, I can multiply on both sides by the inverse matrix. Use that darn associative property for multiplication matrices, which you and I discussed. Reassociate the multiplication with A inverse and A. Now, assuming there is such a matrix called A superscript -1, for which, when I multiply the A on either side, I get the appropriate size identity matrix right back. And one thing you and I did prove in class is that if I take any matrix, like for example the X bar, multiplied by the appropriate size identity matrix, I will get that matrix right back. See guys, all I'm suggesting is that if I have the ability to come up with an inverse matrix, then I can solve the system, well, solve the original system for which this single matrix equation represents. Just by multiplying B bar by the inverse of a matrix A. I just want to come to class today and get better practice using this more sophisticated example. And let me go ahead and rewrite this back in matrix form. This time I'm only going to discuss the coefficient matrix, and I'm going to augment it with a 3x3 identity matrix. You guys, can you just make sure I'm writing this down correctly? Is it 1, -1? 1, 1, 2. But like I said, augmenting this with the appropriate size identity matrix, I will indeed use my elementary operations to reduce what you see on the left-hand side down to the identity matrix. And if I can succeed in doing that, what I see on the right-hand side will be the inverse matrix. Take this with a grain of salt. Not every matrix has an inverse. I might not be able to, for a given case, reduce what's on the left-hand side down to the identity matrix.
So when we're writing that, like for a quiz or an exam, what notation do we use to refer to that as? Do we say like, let me just find the identity matrix by doing this whole stuff?
Yes.
Or the inverse?
Yeah,
Okay.
just say, let's find A inverse.
So that's not equal to something necessarily, that's just how you find
That's true. I'm not saying that everything you see on this board right here is actually equal to something in my equation. It's just a procedure I follow to generate that inverse matrix. So, everybody, allow me. I'm tired. I'm the one doing the arithmetic on the board in front of the entire class, and I want to beat that clock. So, do you guys mind if I avoid fractions as long as I can by not multiplying the first row by 1/2? Just avoid fractions for as long as I can. I'm going to interchange the first and third rows. And I am not touching the second. Next, I will finagle everything else I'm working with in the first column. That would be, of course, transforming every entry not along the main diagonal of the first column to be a 0. I can accomplish that by taking the first row, multiplying by -2, adding it to the second row, using the result as my new second row. Okay, so I got lucky here. I guess it's the same action I'm going to take on the first row before I add it to the third row. Use the result as my new third row. And I think that transforms the matrix I have into this equivalent one, where I've got the first row not changing officially, it's only changing in my head. My second row becomes, is it a 0? Is it a -1? Is it a -5? 0, 1, -2. I think my third row becomes a 0, -4. Is that a -8? 1, 0, -2. You guys, my processes are so simple, aren't they? It's just a lot of bookkeeping. Now for me to work on the second column. To force the entry in that column along the main diagonal would be a 1. You guys mind, here too, can we just use some shortcuts? I mean, if I just interchange the first and second rows, I get a +1. But I shouldn't, why not? Because I've already got a leading 1 in the first row, and I'll goof that up by putting a 1 down here in the second row. So definitely that's not the way I want to go. I think here I kind of step. Can't do anything that sophisticated, so if you don't mind, I'll leave the first row as is. Multiply the second row by -1. And I won't touch the third row yet. However, I do think I can start messing around with everything else in the second column, forcing everything else in the second column not along the main diagonal to be 0 itself. And if I were to do that, I am officially, for the moment, not changing the second row. But in my head, I'm going to do the following. I'm going to take -1 times the second row, add to the first, use the results of my new first row. I will likewise take the second row and finish my sentence.
So that 4 add to the third row, the result of the third row.
I like it. I now have sitting in front of me, whoops. Is that going to be a 1, 0? Is that a -3? Is that a 0, 1, -1? I think my new third row will be the following. How about a 0, 0? Okay, I'll slow down at this point. Is it a 12? And then a 1, and then a -4, and finally, is that a 6? Well, my next step is a piece of cake. I'll take the third row, multiply by 12, use the results of my third row. You guys, I'm almost done. You just let me bore you to death by applying one more step. To force everything to the right of the vertical norm, to truly be the identity matrix, all I'm going to do is take the third row, multiply by something, add it to the second and first rows. How about in particular? Taking 3 times the third, adding it to the first, use the results of my new first row. And likewise, take, how about -5 times the second? I misspoke, I meant times the third. Add it to the second, use the results of my new second row. But I think in the first row, that just gives me, shoot, you guys with fractions. Okay, so I will slow down with the fractions. 3 times this plus this is going to give me a quarter. 3 times this plus this is actually gonna give me a, oh, how nice, just a 0. 3 times this is 3/2, plus a negative 1/2 is positive 1/2. And I maintain negative 5 times 1/12 plus 0 is a negative 5/12. And negative 5 times this plus this is going to give me 5/3 minus 3/3, I think is 2/3. And lastly, negative 5/2 plus 4/2 is negative 1/2. And I've got my last entries not changing. Now I maintain the utility of all this is that I get to take that original system oh no. Oh, here it is. I need my book. So I get to take the original system and rewrite it in matrix form. And I think my solutions for x bar are going to be nothing more than the inverse of this matrix. Times my B matrix, that's why I'm bringing this up, I don't remember what the B bar was. Is it 635? 635 with 2 negatives. But I think that's equivalent. You guys, I know I'm writing too much. Just bear with me for a minute. I want you to see how this works. Take the inverse matrix, which by the way has entries 1/4. Can you guys see the rest? Is it
0, 1/2. Second row, negative 5/2, 2/3, negative 1/2. Third row, 1/12, negative 1/3, 1/2.
Gotcha.
I think it's 5/12.
You know, right here.
Yeah.
Gotcha. And I maintain multiplication clearly is defined. Cheapers, you guys, I got a 3/3 times a 3/1. And I think in the end, it's going to just give me a 3/1. Let's talk about the entries in the 3/1. The very first entry is the result of dotting this row with this column. But cheapers, that's just going to give me negative 3/2 plus 5/2 is positive 2/2. I think dotting the second row of the first matrix with the same column the second is going to give me too much. I can't do it in my head. Is that a
15, 16, 15.
boy? I'm just tired. Is that a 5/2 minus 2 minus 5/2? Oh, how convenient. I think in the third row, that's going to give me a negative 1/2 plus 1 plus 5/2. That's 1 plus 4/2. That's 1 plus 2, which is 3. Did I get my negative sign? My apologies. So I have no idea what got as a solution when I did this the first time last week using Gauss-Jordan elimination. I hope it's the same answer. Yes, Chris.
Is it gonna be the same answer because you permuted your rows?
Ah, I know I did when I actually generated the inverse or the inverse matrix of A. It makes no difference. That was just a process in generating the inverse matrix. It had no effect whatsoever on the final solutions. So like I said, I hope it's the same solution we had last time. It better be.
So isn't this a much longer way of arriving at the same point?
Yeah.
So why'd you do it?
I think this is such a nice approach because I can describe it in terms of a mathematical equation. The AX bar being equal to B bar, I can now rewrite it as X bar being equal to A inverse times B bar. And to me, to be able to say that with a single matrix equation is just more elegant than saying, oh, let's generate this goofy thing called an augmented matrix, and you apply Gauss-Jordan elimination. To me, it's just more aesthetically pleasing as a mathematical process.
Okay.
Can I show you guys how easy it is to cheat with all this? You guys allow me.
So how come all the cheating methods are the ones we can't use on the test?
I just think you might think I'm insulting you.
Oh,
Insulting intelligence. Actually.
All right, everybody, here I go. I'm going to dive in to my matrix command. It's the second example. I'm going to edit a matrix, and I'll call it matrix A. And this is going to be my 3x3 coefficient matrix. Whose entries are 2, -2, -4. Oh, you guys, I don't need your help with this one because it's sitting right in front of me. And there it is. And since I said there it is. And if you guys don't mind, I'm going to go back to my matrix command list. I'm going to now edit the second matrix. I'll edit one named B. I'm simply going to type in a 3x1 matrix, and it's going to be my column vector. And the entries are going to be -6, -3, and 5. And check out how cool this is. When I go back into my home screen, I bring the name of the matrix A, which means go back to my matrix command list, and just simply grab the name for matrix A. That brings it back to my home screen. Watch what happens when I access this command right here. I know it's a reciprocal command in algebra mode, but when it comes to matrices, it automatically generates the inverse matrix command. And if I multiply what I referred to as matrix B, oh, check that out. The computer did all the work for me. Just solved it differently than I did last week. So now you guys really are mad. So do you guys think I can show you a shortcut? If you got a 2x2 matrix, coming up with inverse is this easy. You take the entries along the main diagonal and you swap them. You take the entries along the non-main diagonal and you leave them where they are, but change your signs. And you multiply on the outside by a scalar, which specifically is 1 over the product down the main diagonal, minus the product down the non-main diagonal. That will generate the inverse matrix.
what? How come they didn't show us that in college algebra?
What's that?
I said, how come we didn't learn that in college algebra?
You certainly did learn that in
I
college
did
algebra.
not learn that
Yes,
in
you
college
did.
algebra. No, I didn't.
Where did you take college algebra?
Here.
Really?
No, she just showed us the
We never saw that.
actual long form way of doing it. We never saw. That would have been so nice.
Well, back in algebra, how'd you guys do this? If f of x is equal to ax plus b over cx plus d, how'd you find this inverse function?
In algebra?
Yeah.
All right, let me think. You realize I didn't take algebra with you, right?
No, that's what I'm saying.
True y like x, you swap basically the y to f of x and x's, right?
Wow, sounds like a lot of work. You're right. Perhaps just write down the answer.
Oh my god.
Very similar to that.
Yeah.
I didn't know that either.
Can I prove this to you? Can I prove I'm right?
Go for it.
All right, I'll go for it. You guys, it's time for you to put your feet up, relax, I'll do all the work.
Does that only apply for 2x2 matrices?
Yeah, unfortunately. Good question. So I don't have any tricks up my sleeves with 3x3s. You have to cumbersomely go through the process. But you guys, like I said, you relax, let me do all the work. I'm gonna take my original matrix, A, B, C, D, that already has the right order. And I'm gonna augment it with the appropriate size identity matrix. And I'll play my usual game. Multiply the first row by 1 over A. You guys, this won't take long, there's only 4 slots. I'll force the other entry in the first column, not along the main diagonal, to be a 0. By not touching the first row. But I will, in my head, multiply the first row by negative C added to the second. I said multiply the first row by negative C added to the second. Multiplying this by negative C adding the second gets to this. So I guess just rewriting that fraction that's in the second row, second column. Let me get there, hold on a minute. Instead of B over A, instead of 1 over A, 0, then I got a 0 and a fraction, where the fraction ends up being AD minus BC. All over A. You guys, that wasn't one of my elementary operations. I was just cleaning up that one entry. Now, I think my next step is to force the entry in the second row, second column to be a 1, but that's a piece of cake. I'm just going to reciprocate it. It's that easy. It's just that when I reciprocate it, well, I should say multiply it by its reciprocal, I get the 1 as desired. Unfortunately, this is going to be a little more complex. Is that going to give me a negative C over AD minus BC? Well, I cancel it. And does that give me an A over AD minus BC? And you guys, if I'm not putting you to sleep, I've only got one step left, just one left. So here's my end result. You know I'm going to want to get a 1, 0, 0, 1 on the left-hand side of the vertical bar. On the right-hand side, the second row does not change. It's at a negative C over AD minus BC and an A over AD minus BC. All right, let's talk. We're going to now take negative B over A, multiply the second row, add to our first row, use the result as a new first row. That's my action. But if I take negative B over A times this, and add it to my entry in that column, the first row, I get an arithmetic issue. And I think, arithmetically speaking, I've got a positive BC over A times stuff. Plus another fraction whose denominator is not stuff. But I'll force it to be. By multiplying top and bottom on it. But you guys, when I add the fractions, don't the BC terms cancel each other out? I get a single fraction with that upstairs. When I cancel the A, doesn't it just simply leave me with a D over AB minus BC? I misspoke, didn't I? I meant to say AB BC. And the last entry is the result of multiplying negative B over A to this one. Do you cancel? I just got negative B over stuff. Add it to 0, doesn't that just give me negative B over stuff? Well, I think what I've just proven then is that the inverse of my matrix ends up being nothing more than D negative B, negative CA. Oh shoot, I forgot my fractions, darn it. Well, actually, all these denominators are the same, aren't they? So when I pull out, it shows up as a coefficient on the outside, and I get exactly what I just erased on the board, exactly what I said I'd get. Product down the main diagonal, minus a product down the non-main diagonal. Notice that the A, B, C's, and D's, notice how they get changed. These two are interchanged, and these two stay the same position, but I just change their signs. That's why that trick works.
So nothing that nice pops out for food bakeries?
Unfortunately not, no. I'm sorry.
Is there at least a formula?
If there is one, I don't know it. I've certainly never come across it.
So, you know,
Guys, be honest. I want to answer something else. I want to respond, Chris, to your comment. How many of you honestly remember Cramer's rule from algebra? for pre-calculus?
Never learned.
You never
Didn't
learned
learn
it.
it.
No. How many of us learned it? Oh, shoot. Chris, you never learned it? I'm not trying to pick on you. It's just because you asked a question. All right, I'll save my thought for another half hour when I go through some examples. The Kramer's rule. And then I'll add to what I just said about finding a shortcut. Any questions or comments?
So you don't mind if we just take that shortcut anytime we see an inverse matrices?
I assume you would.
All right, good.
Why go through all the work? Yeah.
They made us in college algebra.
They were hiding this from you, I think is what they're doing.
They're hiding it from me because they were mean. And
Oh my god. You have any boards?
So far, what we have in our back pocket is our Math D skills of using the addition method or Math D skills using substitution. We don't want to discuss those. Let's talk about our new tools. Rewriting this set of equations as a single augmented matrix using Gauss-Jordan elimination to reduce. Or number two, we can rewrite the system of two equations and two unknowns as a single matrix equation and use inverse matrices to solve for x bar, which is the column vector containing my variables. How about number three? Using something called a determinant to solve the system. Today, I'm not being theoretical. I will this week, but not today. I just want to get the tools now. Choose determinants. Here's what I'm going to do.
so
Yes, I'm all ears.
you said that Kramer's rule, in your opinion, is one of the worst ways to solve these things.
I shouldn't say
But-
that. I just meant if you're a computer scientist.
If you're,
you don't
well,
like-
obviously it would be a pain to program something like that, but when is Kramer's rule useful, in your opinion? Or when would you ever use Kramer's rule over the other methods?
I'm trying to fail students.
If I have a diagonal, maybe
Okay.
determinants are really nice. If I have a small system like this one, I think Kramer's rule is very quick and easy. I think it's fast. It just tends to be easier for me to keep track of my arithmetic when I use Kramer's rule because the operations are so easy. Instead of looking at a matrix where I'm multiplying one row by something, add to the next one, in class, I assume I've made mistakes already. It's just easier to make mistakes, I think, with Gauss-Jordan.
'Cause I always found it's easy to make mistakes when you have something that ends up looking like that, with all the fractions.
Yeah, I think from a student's perspective,
Yeah.
you would probably said the inverse matrix method is the one you definitely don't want to use, particularly with a 3x3 system.
Well, now that I know the shortcut.
2x2 is okay. See, guys, let me solve the system using a whole new technique. I call it Kramer's rule. And I'm going to consider the coefficients of x and y. I am not going to create a matrix. I'm going to create a determinant. Notation similar, but I use vertical bars, not brackets. Big difference. Now, when it comes to a matrix, it's a rectangular array of numbers. It's a rectangular array. A determinant is not. It's just a real number. And I will compute this real number. I will compute it by looking at the product down the main diagonal. Minus the product down the non-main diagonal. I think it just gives me -2. Can I give this a name so I can refer back to it? I'll call it determinant. Next, I'm going to go ahead and take this determinant again, which has entries 2, 3, 4, 5. But you guys, this time, can I, with my red pen, can I use my eraser? Get rid of the first row. That is to say, get rid of the coefficient of x, and replace them with the constant terms on the right-hand side of the equal sign. I'll refer to this as d sub x. And let me compute in the usual fashion. 2 by 2 determinants are a piece of cake to evaluate. Product down the main diagonal, minus product down the main non